Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, everybody. It's my pleasure to introduce Dr. Cynthia Wong from CMU. Cynthia is part of the research faculty at CMU since 2001, and her areas of interest is in worm defense and network security, as well as privacy. And she's very into salsa dancing as well.
Just a little bit of different things to talk about rather than all my academic interest. So thank you, Helen. I have a somewhat interesting history with Microsoft Research. When I graduated, I had scheduled an interview here, but because personnel travel and stuff, so the interview didn't get scheduled in time before I took the CMU offer. So I called Microsoft Research and said, "Oh, I'm not going to come up because I already take the offer." And then the week after that, I think I went to a conference and I saw Yi Ming, who's in the same group as you, and which is the group that I was supposed to interview. And he was like, "Oh, you're the girl who declined us. You're on the blacklist now." So anyway, so that's a little tidbit of interesting history. So this work I'm going to talk about is a paper that we're going to be presenting tomorrow at the RAID conference, which is a recent advancing intrusion detection. And this is a systems study of various rate limiting proposals that are out there in the literature right now. We used, it's been like over a year, we've been collecting network traces in our own network, which is an academic department network, and we collected inbound and outbound traffic, headers of the network traffic. And we used these traces to test these algorithms. And the traces also included recorded real worm attacks, true worm attacks. So we're going to use these as a basis to test the efficacy of these different algorithms. So just to declare beforehand, we did not do any analytical modeling here. It's a pure system study. The purpose of this study is just to see how these different proposals might work in practice with real networks. Let me try this. Okay, so very simple. Rate limiting works by limiting the contact rate of hosts or subnet in a way that restricts a little bit of, now this is, okay. I haven't mastered this thing yet, so might be a little bit glitch. So the rate limiting engine sits on, say, the network link of the host. And the way it works is by looking at the contact rate of the host. And some of them will get through, some of them will basically drop it. For instance, drop it or delay it so that to maintain an acceptable contact rate of hosts. Why they do that? Because worm-infected hosts, for instance, would have the signature of having a abnormally high contact rate. So the scan traffic of the host once it's infected is abnormally high, and it will contact a large number of hosts. So rate limiting works by restricting the contact rate, hence restricting the spread of worms. Okay. So rate limiting mechanism can work on host level, which is you have this algorithm running on every host. Or you could work on the gateway level, which is try to rate limit the contact rate of a subnet. Okay, so we're going to analyze both of these approaches in this study. So the three different proposals, recent proposal we're going to analyze is Williamson's virus throttling, and Chen's failed connection-based throttling mechanism. Ganesh here is familiar with all these, and he's also done some analysis work on these rate limiting mechanisms. And Schechter's, which is in last year's RAID conference is on a credit-based throttling mechanism. So all these are throttling in a way that restricts the contact rate of hosts. So these mechanisms all work on slightly different parameters, just network traffic parameters, but there's no comparison study thus far. So this work basically is to put them direct head-to-head comparison with same traffic and same attacks, and to see if one is more effective than others. And we also, in this study, included one of our own proposal, which is a DNS based rate limiting. We're going to rate limit the contact rate of the host or subnet based on the behavior of the DNS traffic. Okay, so I'm going to talk about each of those in a little bit detail. Our goals, using real traffic trace to analyze rate limiting mechanisms, and like I said, the direct comparisons, and we attempt to study some fundamental aspects of rate limiting, but again, this is not an analytical study, so all these conclusions are inevitably influenced by the peculiarity of our traces. So take it with a grain of salt, basically. So the trace data we've been collecting is from a network sort of look like this. This is the place that we've been collecting the border traffic. We collected all the inbound and outbound traffic from our network, and think of the everything that below this gateway is our department network, and it's about a 1,200. We have a 1,200 externally routable hosts of this network, and we've been collecting over a year, actually more than a year, 2 years of traffic. Only headers, no payload. And within this trace period, we recorded blaster and Welcher infection within the network. And these worm attacks infected about, I think it's 100. In the end, we determined 100 infected hosts within the 1,200 host network. Let's see, this network serves about 1,500 users, and it's a fairly open network in the sense that there's no strict traffic policy. We don't have firewalls running anywhere, and people run their own web servers or different types of services on their desktop. It's not a enterprise or corporate tightly controlled network, basically. That's about it for the network traces. So this is the trace volume that we observed during the attack. For the study, we're going to use I think it's 25-day long trace. As you can see, that blaster hits on the 6th day of this trace, which is, I think, August 13th or something, 2003. So, and then Welcher hits our network, I think, 7 days later or something. So as you can see, the traffic volume, this is outbound traffic that we recorded at the gateway of our network. It increased about 20-fold also during the first day of the attack, and it sustained that high level for a few days, and then eventually died down after about 10 days or so. Okay, and that's at the end of this trace period, we saw some residual activity of the worm, but for the most part, we see things start to get patched up around this time. And this period is when, this is the end of August, and students come back to school, and more desktop being turned on, and there's a little bit more instances of worm being introduced into the network, and you see a little spike here. Okay, so this is the trace we're going to use. The experiment methodology we're going to use, rate limiting, for the most part, works on individual flows. So the rate limiting engine processes each flow packet, but think of it as flows, and decide whether this flow can be permitted through, or delayed, or dropped. Okay, so we're going to look at 2 different parameters: false positive rate, the percentage of normal flows that are delayed or dropped, okay? And false negative rate, basically the percentage of worm flows that should be delayed or dropped, but it's not. It's permitted through without delay. So this is our definition of the two parameters that we're going to study. And again, we did not study the performance and memory overhead of these different schemes because we have our own implementation, and it's a bit hard to actually do a study on what the performance overhead is because our implementation is quite preliminary.
So will you tell us what these different methods use to recognize the worm?
Yes, I'm going to go through each of these different methods. Now what? Okay, I have a misorder of the slide. Sorry about that. But we're going to go through this one first. So Williamson's, the first mechanism we analyze is Williamson's virus throttling, which is proposed by Matthew Williamson of HP Labs. And this mechanism is now in some of the HP products. I don't know which exact product they have this algorithm, but what we studied is the algorithm that's in the public domain. So the ones that implement in their product set is maybe slightly different, which we do not know the details. So this is the Unix 2002 paper. So what they do is Williamson's scheme operate on this observation that normal hosts have a fairly stable contact rate. Okay, so your desktop may be contacting 5 different IPs every second, or maybe every 5 seconds. I don't know. But if you observe the normal operation of desktops or servers over some sustained period of time, you'll see a somewhat stable contact rate in terms of how many distinct IPs this host is contacting over a period of time. So this rate limiting mechanism operates under this assumption and trying to limit the rate of fresh IP contacts of a particular host or subnet to a certain level. Okay? Now this is how it works. This rate limiting engine keeps a working set of addresses. Think of it as cache for each host at the host level. And this records the 4 or 5 different IPs that you contact often. And every time when a packet comes through, a SYN packet, let's say, if it's in the working set, it's permitted through. If it's not in the working set, it puts in a delay queue. Okay? And once every second, which is the rate they proposed in the paper, but think of it at a static rate, packets that are delayed in the delay queue gets processed and gets sent out. Okay? And if the delay queue is full, when there's more packets coming into the delay queue, when the delay queue is full, the packets will simply get dropped. Okay? So the net effect of this scheme is that contacts to addresses that you repeatedly contact is going to get permitted through without delay, while things that you have not previously seen will get delayed or possibly dropped. And this is a way to limit contact of worms, because worms usually go to scan destination IPs that they haven't seen before. They're doing a random scanning or sequential scanning of IP space where most of these addresses are not external servers or desktop clients that you've contacted before. Yes?
Aren't there legitimate behaviors that are adversely affected by this approach?
Yes. So the study is to see what the false positive rates are. And legitimate behaviors, yes, indeed. They are, if you start up a new application, for instance, you will be contacting addresses that are not normally in the working set. So the premise of this is hopefully it should not affect the normal operations that much. Things might get delayed a little bit, but hopefully not by much. However, the worm traffic will largely get delayed. And let's see if that's the case. So, okay, I'm sorry about that. I'm going to have to, have a misorder of the slide. So this is the false positive results that we implemented Matthew Williamson's scheme, and we took host traffic, and we implement this algorithm on each host. And this is the average result you see on infected hosts, the 100 infected hosts in the network, and false positive rates. So remember, blaster hits on the 6th day. So before that, you see about slightly less than 20% of the normal flows are delayed. Now, the delay statistics, you don't see it here, but they delayed about, I think it was 5 seconds on average. So a lot of applications can tolerate that level of delay without causing too much problems if they're not hard real-time applications. However, when you see when the blaster hits, the traffic volume went up. This is at the host level. You see false positives go up to almost 100%. So what happened there is the delay queue get quickly filled up with worm packets. And new legitimate traffic simply just could not get through and either dropped or get delayed for a long time. And the delay queue size in their paper, they recommend 100 addresses as the delay queue size for each host. And that's what we implemented here. And this is what you see when the worm hits, almost everything is delayed. Okay? Yes?
So it's identified as a worm when it hits the delay queue?
No, it's not. Actually,
delay queue.
that's a good question. How we identify things as worm. Because we only have 2 recorded attacks, blaster and Welcher, that we know for sure. And we know what port numbers these scan traffics trying to contact. So we look at, we do post-mortem analysis of the network traffic, and we know this machine was infected at certain time. And we look at all the traffic, outbound traffic from this machine after that time and say, okay, it's for blasters port 135. And if it's port 135 traffic, and if it's contacting a lot of port 135, we label them all worm flows. So we sort of lucky in the sense that the machines in our network mostly all window machines. And port 135 is a port that window machines almost never use. And so you see a drastic difference in the behavior. Before the worm hits, these machines rarely, if ever, make any port 135 outbound connections. And after the hits, it makes tens of thousands port 135 connections.
So you label it a false positive when an innocuous flow, its packet drops from the
Dropped or delayed. So I need to clarify that a little bit. So in the delay part, some of the packets are not delayed that much. But in order to be sort of fair for all the different schemes, if it's delayed at all, we call that a false positive. But I'm going to present statistics later to tell you how much are delayed and how much are actually dropped.
By delayed,
Yeah.
including the 1 second or so delay?
Yeah, include the 1 second also delay.
Okay.
Okay.
So
Yes.
Why doesn't the graph drop off back to sort of pre-blaster levels as time increases?
I think what happened is that's a good question.
I thought that from the previous graph, it looked like you still had lots of blaster infections 20 days later.
We had some residual effect, but it wasn't. I think what happened is the delay queues, if they're not cleaned up in any way, they just keeps going. Okay, and this is actually this is me going off deep end thinking that is the case. So if the delay queue is maximum and you keep getting traffic that's more than 1 second, 1 per second, which is the rate that delay queues gets dequeued, then your delay queue size will stay full. You know what I'm saying? Over the period of time that the trace is being studied. And I think this is the behavior that we're seeing, but I'm sort of...
It doesn't make sense, though. Even if that were the case, if your blaster levels had decreased to a point where they were roughly at the time prior to infection, which your previous graph showed although there was a slight increase, then even if the delay queues maintain the fact that blaster was there, then normal traffic should have overwhelmed the small amount of blaster traffic.
No. So at this point, the normal traffic and the worm traffic don't make a difference anymore. At this point, what makes a difference is if the new traffic comes in, the rate is over 1 packet per second, which is the rate that things gets dequeued.
Why don't you update your list of legitimate addresses, etc.?
Yeah. So this is the algorithm does not do that. Okay. Yeah. So
the whole year you only have 4 addresses.
No, not whole year. So I'm sorry. That's one thing one detail I forgot to mention is the working set. You do update the working set in at least recently used algorithm manner, and at the same rate that the packets being dequeued. Okay. Every time a new packet being dequeued, you replace the recent used address in the working set, and you put the destination address of that dequeued packets into the working set. So if you are dequeuing at a 1 second, 1 per second, and the addresses in there are not, basically it's going to get filled up with all worm packets.
One last question.
Yeah.
What is the size of the queue as opposed to the working set?
100. Queue is 100. 100 IP. And the working set here, well, this is active set, which is basically the working set. So the length is from 4 IPs to 10 IPs, and 5 IPs is the recommended value by Williamson. Yes?
So how adversely affected are the applications?
How what?
How adversely affected are the applications when a machine is infected with one of these worms, where you keep dropping packets from these legitimate applications?
Right.
Do the applications just stop? Or what is the performance? What do you see from these applications?
Yeah, so that's one thing that we don't see here, because we did this on the trace study. Now, if you were having this algorithm running in a real network, what you see is basically the whatever the application behavior is when you cannot connect. Okay, and sometimes I think what we've observed even in the a TCP session in the middle. You hit if the worm hits in the middle, and the rest of the session basically just get dropped. Yes.
The attackers can potentially game this approach.
Yeah, absolutely.
By sending traffic to the same address for a period of time.
Yeah.
And then in that case,
so it's
very high false negative.
Yeah, if the scanning traffic is using the same address over and over, then you get false positive rate. But worms don't usually do that, right? So they're sending scanning traffic to the same host, which don't gain much benefit for them.
But how can it game it? I mean, it can only infect 4 machines. After that, it's sort of done, right?
But you keep sending the traffic to this. You can still send the traffic to the same machine, although it doesn't impact it.
Right.
To game your system, just to game this.
Yeah, but once you try the next 4, then it will take a while before it's updated, so it slows you down.
It definitely slows you down. Yeah. Yes, it slows you down to once the working set is full, it slows you down to basically 1 address per second. So substantial increase in false positives as worm hits, basically. And I'm going to do this so we don't have to go through the sorry for this. Where am I right now? So we'll do this. Okay, this is the false negative results, which is also on infected hosts. And no, before the infection hits, it's 0, obviously. And this is the time, the remaining time of the trace after infection. And the false negative results are fairly good. It's not bad. Okay, you're letting out, but 1% or less of infected traffic, basically. So, no questions there. This is a little bit dissected statistics of delay queue size in this statistic. So as you see, which, yeah, I think this is correct. That's why we don't see a false positive coming down. Is the delay queue, once it's full, it keeps, it remains about 90% full for the rest of the period of the traces. And this is the delay versus dropped statistics. And I think this is for, let's see, how long is the, this is for a 3 hour? Do you remember? This is for a 3 hour trace or something? Yeah, okay. So I don't remember how long this period is for, but as you can see, the total number of traces are basically this number plus this number. Total number of traces are this number plus that number, okay? So we have dropped and we have delayed. And for this, I think this is for the first day of infection, if I remember correctly. So you can see that benign traffic, a lot of benign traffic were delayed for 90 seconds or more. And the malicious traffic, a lot of them are also delayed, which we see false negatives is low. And many benign traffic, legitimate traffic is dropped. Yeah?
Once all the machines were infected, did you just leave them infected?
I'm sorry?
Once the hosts were infected at day 5 or day 6, did you just leave them infected?
So what happens is the machines do get patched within the trace period. And once the machine is patched, we remove it from the infected host pool. In other words, they do not factor into the average statistics after that. Any other questions? So basically what you see here is once the machine is infected, the legitimate applications are basically stopped, blocked. Just a few sentences of a conclusion. Normal operations are, during normal operation is fine. It's 3-second delay, no big deal. During infection, scan traffic quickly fills up delay queue, and you don't have much left. But one thing good about this is it has a very simple algorithm. You can easily implement it, and it's a fairly elegant approach, we think. But it boils down to a detection and block behavior. Basically, you can say that if the delay queue is ever go beyond, say, 50 addresses, pretty much your machine is infected. At which point you can just take the machine off the network and cleanse it rather than leave it running. And so it's not much better than detection and block behavior because no other things can run anymore after that. So as I said earlier, rate limiting can be deployed on individual host or aggregate. And just for fun, we implement Williamson's on the aggregate level, which is at the gateway. So we have a set of working set addresses for the entire network, which is 1,200 host network. Now, it only makes sense if the gateway level rate limiting, the addresses you keep is not linear increase to the number of addresses as with respect to the host level. So what we did is the address set is for the whole network. We did 10 to 50. Okay, and aggregate level throttling is kind of attractive in the sense that single point you have to instrument, and it's basically less state you have to keep. You keep for the entire network versus at each host level, and as you can see, it's pretty bad. And this is to be expected. We just wanted to see what the results are. And this is aggregate for false negative aggregate, and yeah, false negative is still good because for the entire network, nothing can get out basically, including the worm traffic. So the second, yes, question.
Question about your false negative graph.
Yeah.
So how long would Blaster take to infect the internet if the false negative rate is 0.5%?
False negative rate is 0.5%. So Blaster, in our data set, Blaster scans about 20 to 50 scans per second. Okay, and if you think of it as random scan, then it's the hit rate is fairly low. Now, if the false negative is about 0.5%, it does not do a lot to the hit rate. It does not change the hit rate or the miss rate that much. That's been our experience, although I have not done any actual analysis on that. So. The second algorithm that we analyzed is Chen's failed connection-based rate limiting. And this is a paper published in ICDCS last year. So this, I keep looking at that guy over there. You look very familiar. Yeah. Where are you from?
I work in the kernel team of virtualization and previously on NGSCB.
CMU?
I didn't go to CMU, nope.
No? Didn't go to CMU? Okay. Must be somebody who looks just like you. So the fundamental observation behind this scheme is because worms are doing random scanning, so most time the hitting address is not there. So they generate failed connections. So this algorithm, instead of trying to limit how many fresh IPs you can contact within a period of time, it tried to limit how many failed connections you can generate. Okay? And so the algorithm works as following. You know, I'm sort of at loss of these animations. So as sync comes through, the rate limiting engine basically hashes the source address of the SYN and put it into a collision-free, not collision-free, collision-full hash function, hash into these buckets. Basically, different hosts are in the same bucket. And you have a threshold of failed connections you can generate for each bucket. And if the connection number of failed connections exceeds this threshold, what you do is you take all the source addresses that are generating these failed connections, put into these leaky bucket algorithm-based rate limiting. And the way it works is each host is allocated a certain number of tokens. And every time a failed connection, you initiate a connection that's failed, you consume a token. Okay? And tokens are deposited back at a static rate, and 1 per second, for instance. Now, what this does is if the connections that are coming through being rate limited are mostly worm connections, they will generate lots of failed connections rapidly, hence depletes entire tokens in the bucket. So once the host does not have any tokens to make connections, it basically stops. The rate limiting engine says you cannot make any connections until next time a token comes available. And the token comes available next time it's deposited in. Okay, so this is how the rate limiting works. And so this is what I just said. Okay, so the error rates of this, we term it FC, so it's for failed connection based. False positives and false negatives. So what are the, Ahren, what is the confidence interval of these data points? Do you remember? Don't remember. Okay, well, that's the average. False positives and false negatives. You see that the false positives are before the infection are comparable to Williamson's. After the infection is much better. No, it's not like 90%. And false negatives are not as good. So this is an algorithm that works on failed connection only. Basically, if you have repeated failures, what we see is these false positives are due to, for instance, a protocol that's connecting the external server that has a temporary down. And you retry the server repeatedly a few times, and all these failed connections are being considered in the token consumption. So that is why one of the primary reasons for false positive. And this is some of the basic detailed statistics. You see that, let's see, that those are the top two false positive generating addresses. Both of them are peer-to-peer, okay? And it's not unexpected because peer-to-peer tend to generate failures. Yes?
Would you say the false positives are a result of collisions in the hash buckets?
some we saw is due to collisions in the hash buckets, but it's not a primary reason because if, say for instance, you are a normal host and you get hashed into the same bucket as someone who's infected, right? And then you get rate limited. If you're a normal host, then most likely your behavior or failure behavior will not result in a complete depletion of your tokens. Okay, so you can still do normal connections at a rate that is not too far from that you're not rate limited, basically. So it's not a primary reason. Yeah.
Which one of the addresses were hashed, the origin or
the source? The source.
Aren't false negatives because the network got really busy, so there's a lot of
false negatives because the network is busy.
So when Blaster consumes all the network pipe, then they can't connect for peer-to-peer, for instance. They time out because the network is busy.
But that wouldn't be false negative. False negative would be.
Oh yeah, so you're doing normal bear share traffic, but the
that's
network's
false.
busy. Well, that's false positive.
Yeah, that's false positive because we consider everything, including peer-to-peer, legitimate traffic. Okay, the only worm flows are bad traffic. So peer-to-peer is actually considered in the legitimate traffic pool, and if they are dropped or delayed, they are false positive.
But this mechanism can be gamed by changing your IP.
Can what?
Is this mechanism? Is it possible to game this mechanism by changing your IP?
Source IP?
Yeah.
Yeah, possibly. Possibly. So what you can do is you can try to, if you know the hashing function, and you can try.
You don't even have to know it, right? You change it. And
yeah. That's right. You don't even have to know.
Yeah. You can't propagate the worm.
Yeah, but then it's an administrative
it's a SYN
network.
Attack. It's a SYN attack. You can't do it. You can't propagate. You can't open the three-way, right?
Maybe you could just call DHCP to re-register.
Well, you could actually, if the worm is smart, you could do some rerouting in a way. But, it's not easy.
Are you comparing like the track in terms of is a false positive in this case the same as a false positive?
Yes. Yes. What do you mean? It's the way we term one is false positive or not is the same. Did I answer?
Is the same length of delay, or is there? I mean.
Okay. So this one, actually there's no delay, right? This one, what the algorithm does is if you have token left, the connection gets through. If you don't have tokens, it get dropped. Okay, so dropping is what we term as false positive here. So in that way, it's not the same because Williamson's has delay and this one does not. Yeah,
and so the remaining set of false positives, as the table indicates here, benevolent applications will make lots of failed connections, I guess?
Yeah, so this is if you look at the HTTP client, which we will come to revisit the same client for a different mechanism. This one is a bursty web client and is one sort of stood out in our trace because it kept contacting a remote HTTP server that is down for a while. So it generated the bursty failures. Then it came back in. The server came back on. So this is one that was problematic for a lot of mechanisms. And the burstiness of it was a problem for this particular scheme because it penalizes failures to the same address. And basically it depletes the credit or the tokens much faster than another scheme you'll see later. Any other questions? So the third scheme that we analyzed is a paper published last year in RAID. It's similar to Chen's scheme, but has a different take on how tokens being allocated. So it's every machine is rate limited using basically a token-based algorithm. And the way that tokens are depleted and awarded is as follows. If you have each connection goes through, you consume a token. And if the connection fails, you do nothing. Basically, you consume this token. If a connection is a successful connection, you add a token back. You add 2 tokens back in. So the net effect is a failure consumes a token, a success adds a token back in, okay? As opposed to Chen's scheme, the tokens are rewarded back in a static rate, regardless of the host activity. But this one, the tokens are rewarded based on host activity. So the assumption is that there appears to be a bimodal behavior between the the normal hosts and the infected hosts. Normal host seems to be making successful connections, even though they may experience bursty failures once in a while the infected hosts are, in general, do not make any successful connections because it can't get out, basically. So that is the way that this rate-limiting engine trying to work. And failure consumes success generates 2 tokens, actually. So it generates a token back in, basically. So this is, another distinguishing feature of this algorithm is that it uses this concept called first contact versus Chen's, which is every failure affects the token balance. This one is only failures that are generated to an address that you have not seen before, so which is called the first contact. And in order to do that, each host maintains a state called previously contacted history, which maintains about, in the paper, they recommend 64 addresses. For each host, you maintain 64 address PCH, which records 64 destination IPs that you have seen in the past. Okay? And this can be done in ways that make it efficient. You could use Bloom filters or hash tables, whatnot. So it doesn't require a lot of memory overhead. So every outgoing connection, the destination IP of the connection is compared with the addresses in there. If it's already in the address, you don't process it, let it through regardless. If it's not in the address, then you monitor it. So the failure or success of that connection, which is the first contact connection, will make a change in the token balance. And that's the difference between this one and the others. So the end result of this is hosts are not penalized for repeated failures, as we see that happens a lot with legitimate applications. So this is the error rate of the host-based, and it's a lot better. The false positives are a lot better than the previous schemes. It's below 10% for the most part. And these false positives that we've seen, from the first day to the 14th day or so, are due to, most part, when we take this apart, are due to a lot of peer-to-peer traffic happen to be heavy in that period of the trace. And the peer-to-peer traffic generates a lot of failures to different addresses, which in the way depleted the tokens more so than others. So that's the result of the false positives. Any questions here? Yeah.
Do you see the effect of changing the threshold? If the balance was -1?
The threshold of the token. So we did experiment with that, and it appeared to have very little effect, for the reason that the initial balance of the token is only approximates how many failures you can generate, independent of the successes. Okay, once you have successes in the background, it generates tokens back in, so it really does not affect that much the initial balance of the tokens. Any other questions? So we tested credit-based also at the aggregate level. So we maintain a PCH for the entire network versus a PCH for each host, and in the hope that you will keep less state and while still have acceptable accuracy. And the result is, I would say it's not too bad. Okay, so yes, the false positive is kind of high, 20, 30%. So these are actually, the false positive here is actually dropped traffic, so it's not as, so for Williamson's actually delayed, so it's not as good. But the in terms of the aggregate level, having this level of false positives, we think are a lot better than the other schemes. So that's what happens at the edge router. And again, that's some results that we took out. And the first two, again, the same same peer-to-peer clients that generate a lot of false positives, the top two false positive generating address. And look at this. I singled this one out just for comparison. The same HTTP client that you saw with the previous scheme, where for the previous scheme, I think it was maybe 50% of the traffic flows were dropped. And this one, there was 0. Okay, so the burstiness, the bursty failure of this particular HTTP client does not appear to be a problem for this algorithm for the reason that it uses first contact rate limiting versus rate limiting on strict failures. Okay?
So even though you only had 64, right, you might think that an HTTP client needs 10,000 addresses or so because it uses so many legitimately.
Yeah, so I don't know. I mean, for an HTTP client, I don't know. For a peer-to-peer client, I would think you would need larger PCH. Obviously, if you have infinite PCH, you're going to get the best precision. But there's a point at which you say, okay, the precision beyond which this is just not worth for keeping all these states. This is for the day 6, which is the day that Blaster hits. So what we've seen so far, the 3 different schemes that we analyzed, we plot them on a ROC curve, and these different points are generated using the different parameter settings. So for instance, for Matthew Williamson, we tested for the working set size between, I think, 3 to 10. And these are the different points that's generated. And this is the credit-based scheme, which is by Schechter. And this one is the one that uses first contact and also uses success behavior along with failure behavior as the basis for rate limiting and appears to be the best performing of them. Okay, and I guess this is Matthew Williamson's. And false negatives really low, but false positives really high. And don't worry about the FC basic and temporal. They're just 2 different parameter settings. I'm not going to explain here because it doesn't really make a fundamental difference. What have we learned so far? So the first contact appears to outperform others because the way it deals with repeated failures. Failed connections only, as the rate limiting parameter is too coarse a parameter to do rate limiting. And the last bullet, dynamic versus static rate. So the scheme here, the only scheme here that gives rise to dynamic rate limiting is the credit-based, which it considers success as well as failures. So in that particular schemes, the rate of traffic that's permitted through is actually dynamic versus the previous 2 schemes are static rates. Yeah.
Do you know how much of the success of Schechter's scheme is due to first contact and how much is due to the dynamic rate?
Do not know. Did not do that analysis. But I can speculate. Let's see. How much is due to first contact, how much versus dynamic rate? I would think, because we experimented with different PCH sizes, and the effect on the precision was less than if you had deposited the tokens back in at a static rate. So I would think, based on that observation, dynamic rate is more effective a measure than the first contact.
It seems like the dynamic rate is easy to gain now.
Yeah, it's easy to gain, but so this is the result of this study is due to the simplicity of the worm that we have, right? So this Blaster and Welcher is fairly simple, fast scanning worm. It's not intelligent. It doesn't try to game any system. So in the future, if we want to study intelligent scanning worms where it try to game the system, then the dynamic array, yes, it's going to be basically opens more doors for you to game the system. Okay, so the last one that we analyze is a scheme that we proposed in this paper, the concept of which is not due to us, but due to a colleague of mine who had made this observation that scanning worms generate direct IP connections. So you generate an IP and you connect to it, and you don't bother to do a DNS translation first. So you look at the traffic, there's no prior DNS translation. So a rate limiting parameter can be rate limit direct IP connections, and don't bother with the others that have done the DNS translations. So how would one implement this? If you were to do DNS-based rate limiting, if you do it at host level, what you have to do is you have to keep host level DNS translations locally, right? And respect the time to live field and update as needed. And you have to monitor the DNS lookups, new DNS lookups of this host. At the gateway, you have to mirror the DNS table of the entire network at the gateway level, and you have to monitor inbound and outbound DNS traffic, and you have to record the result of new DNS lookups. And it's a little bit tricky because sometimes when you look up, say, MIT.edu, what you'll get back in the bundle the IP address of MIT and the IP address of the mail server of MIT, and perhaps the IP address of some other server you'll contact often within that domain. So you have to record all these addresses. And you will monitor this traffic and update the DNS server and basically respect the TTL, and then you can determine whether a connection is direct IP connection without prior DNS translation or not. Yeah.
So can you just whitelist what's in the DNS cache, what's in the local DNS cache of the box?
Yeah. So if you do that, so every time a connection goes out, you have to talk to the DNS server. So this way, I think it's better to do it at the network level, which is the gateway process, versus talking to the DNS server. Is that what you're asking?
No, on the local machine.
Uh-huh.
If it caches the DNS responses,
right.
So it doesn't have to do a DNS lookup for every query.
Right.
So if you just whitelist
this is what the DNS table is. Okay. It basically is a DNS cache. So you mirror the DNS cache that are relevant to your own host at the host level. If you were to do host level rate limiting, and you mirror the DNS cache for the entire network at the gateway level. Yeah.
Is your gateway-based system only for egress points, or is it also considered ingress level infection?
So right now it's only for. So we only do the monitoring goes both ways, and sure. We record all the DNS traffic in and out.
But
okay.
In and out of
but
egress points.
Yeah.
But not for ingress level subnets.
No. So you're going to see some results for the gateway-based algorithm where you don't see any of the internal DNS traffic. Basically. So this is the algorithm that we implemented in the paper. This is what we call a cascading bucket algorithm. So at each time interval t, we allow q distinct direct IP connections, and when you have more than q within this time t, you're cascading into the next time interval, okay? And when the time goes to the boundary of this, you let all the connections that delayed in this bucket through, and the rest is getting cascaded into the remaining time interval. And the maximal interval that we do is n buckets. So n times t is the maximum delay for each packet, beyond which gets dropped. Okay, and then when everything's done to the end of this time interval, we reinstate n buckets. Okay, so why do things in such sort of complicated manner? we talked to sysadmins, and we think this kind of cascading bucket parameter setting actually provides a useful abstraction for them. So what they can say is, what is the maximum timeout period that I want to see for legitimate traffic? And you can set n times t as the TCP timeout period. Okay? And then you can say things like, what is the policy? I want to allow 5 new direct IP flows every 30 seconds or every 10 seconds, and which is a way, happens to be the way that they think. So this bucket scheme provides that abstraction for them to define policies. This is the error rate that you see, false positives for n-host DNS rate limiting. And you see that for the different parameter settings, the false positives is low. And it's around 1% or lower. Okay. Yeah?
So in this case, false positive is packet is dropped?
False positive is packet delayed. And this is delayed or dropped.
Okay.
Okay. Because this has a cascading bucket, so it could get delayed to the next interval. So if it's full.
Did you consider using the cascading bucket for Matthew Williamson's?
No.
Okay.
Yep. Oh, okay. All right. So the false positive, false negatives, 1, 2%. Okay. Results, normal host, basically infected hosts. Let's see, benign traffic is primarily no delays. For malicious traffic, is primarily delayed for very long period of time. Okay. This is just another graph to show you. About 80% of worm traffic in this scheme, DNS-based, are delayed. Another 20%, 80% are dropped. Another 20% were delayed for, I think for 1 minute or longer. Okay, this is the end result of the trace, and this is acquired with Q equal to 10. So 10 direct IP connections per 5 seconds. We also, interestingly enough, implement this at the gateway level, at the aggregate DNS rate limiting, and look at the false positives, low. False negatives for 2 different parameter settings, really low. For one of them, which is the 100 distinct IPs per 5 seconds, this is pretty liberal allowance. You see false negatives hit fairly high. So this is a very interesting result for us. This is a feasible way to do aggregate rate limiting. We can train these parameters based on, observe the traffic for a while and to say how many distinct IPs per 5 seconds or 10 seconds you would allow for this network.
But can you go back? Because I would like to know how you would train it if you don't know about the attack yet.
If I don't know the attack?
Well, because you want to train it before actually the worm is there,
yeah,
right?
Yeah.
And so there would have been no way for you to train it up to day 10.
Day 6 is.
Right. So there would have been no way. I mean, from this picture, what would you choose for your parameter?
So what you'll have to do is look at the network traffic and let's say you do diligence and determine that to the best of your knowledge, there's no infected host in your network. Okay, and then you observe what are the direct IP connections out of your host. So these are mostly due to direct server connections, FTP using direct IP addresses versus server names. The very limited type of applications would have direct IP connections. So you could see what is the normal statistics of the rate of these direct IP connections, and then set your parameters that way.
I see. So you can't just do it from observing this aggregate traffic, but you really would have to look into the details to see.
You could do the aggregate traffic if you kind of sure that there's no infected host in your network. But to be sure, you really would have to dissect each traffic and look at what type of applications are actually running these direct IP connections. So I'm just going to run through. This is overall comparison. That's where the DNS host-based rate limiting is compared to the others. And that's the aggregate rate limiting, so this black line. So that dot is not so great, but this parameter setting here is acceptable. So we think the DNS rate limiting has a very promising way to do aggregate rate limiting. Yeah, I'm just going to go through that. Limitations. So what are the ways that worms can do to bypass this? There are many different ways. Okay, so we just thought about a few, and we can talk through them. Reverse DNS lookups. Or set up a fake external DNS server and connect to it as if you're doing a DNS lookup, but in fact you're not, right? And you just use the port. What is the DNS port? 20 something? 23? 50. Okay. Yeah. So the reverse DNS lookups are kind of easy because they're only limited applications would do that. You could whitelist them. The fake external DNS servers, because people inside the network might use external DNS servers, so you have to know what they are and whitelist them, and that could present a problem for Soho users, who come into your network and just use their external DNS server for a day or two that you don't know about. That could be a problem. So this scheme really is good for enterprise networks have strict traffic policy, but however, because the traffic trace that we got is from an open network, and it also has fairly good result, we think it's really promising. So, yeah, so the advantage, one of the advantages I want to point out is it's really easy for worms to automate probing of numeric IP addresses, but it's not very easy to probe DNS namespace, to automate that, and that's the one of the primary advantages of this scheme is it forces the worms to not do the numeric scanning, and which set this scheme apart from others. Yes?
Except in IPv6, it'll actually be easier to do DNS probing.
Yeah, probably. So this is within the current.
Just for now.
Yeah, for now. So. I'm not going to go through this. So the next slide is one I stole from Ganesh's paper. So if you use an epidemic approach to look at worm spreading, and Ganesh used, sorry, I should credit this, but I made up this slide just an hour ago. So this is the time evolution of R, which is the population of infected hosts within the network. And the theta t there is an additional parameter, which is the what you call the countermeasure reduction factor, right? So what one can do is, in fact, he's doing that, is taking these different countermeasures, say Williamson's or Chen's, and model the theta t as the effect of these rate limiting or throttling mechanisms on the spreading rate. And you could put this into this framework and analyze what the eventual spreading rate is for the epidemic, which is the worm. Now, what we're interested in doing is dream up intelligent worms in the way that the theta t is going to be fairly low, which is the countermeasure, the reduction factor is low. So the intelligent worm will study your rate limiting or your throttling mechanism and dream up ways to bypass it. And we wanted to do a game theory kind of study to see what kind of countermeasures that you can change your parameter dynamically based on traffic rate, and what kind of worm behaviors they can change dynamically based on the observation of the throttling schemes, and do a game theory study that way. So that's an interesting future work of my own interest. So if anybody has any thought, I'd be happy to talk to you. and that's contact information. The project that comprises of is a bigger project, which this paper is part of, is called the Coral Project, which I'm the lead. And you can go to that website and get all the other papers that we published. And our security group of CMU is called CyLab. We have a lot of different faculty there and different research projects going on. You're welcome to take a look at what's going on there. And if you have any additional questions, I'll take them right now. Yes?
I think this was actually a very nice presentation from the standpoint of comparing the different mechanisms. One point, which kind of some of the questions alluded to, which I see missing from a lot of these rate limiting presentations, is sort of the impact on the end user with respect to the false positive rate. So you track the percentage of false positives, from 5 to 90%, but it's not actually tracked in terms of, what does this do in a real environment? Can a user actually not use his machine, or is it just, 1 in every 10 IE sessions?
Right. So we're kind of hampered in that kind of analysis because the traces we have are anonymized. So we cannot trace back to individual machines. We can kind of tell by the protocol number what kind of protocol it is running, but we can't really trace back to, is this a server, or is this a client, or that sort of thing. So it's hampered a little bit in that way. But you're right that we need to understand the impact of these schemes in practice, which is a little bit a step beyond what we've done here, which is just looking at relative precisions, rather you want to look at the effect on end user behavior.
I understand you can't get that information from your retroactive data, but I think that's one of the things that's preventing some of these mechanisms from making their way into mainstream products, modulo the DHP work, which was implemented years after Matt's initial.
Yeah, I know.
And if you compare that to AV technology, antivirus technology, which has a comparatively lower false positive rate and a higher false negative rate, but it's much more reactive. But it is technology which can't be implemented, can be shipped, versus I think this type of technology, because of it's a bit sort of more opaque in terms of what the actual impact of the user. That's kind of what's blocking.
Yeah. So the hope is the hope of proposing this DNS-based scheme is it impacts end user less, because the number of applications that actually do direct IP connections are not. It's not common that you do that, and so that's.
It's a pretty broad statement to make, though.
Yeah, it is a broad statement to make. Yeah, so we have seen user desktops that set up their own web servers and talking to other web servers, direct server to server connection and that sort of behavior. And really, this is an academic network, so people do all kinds of things on their desktop, and that results in some of the false positives that we've seen. But in a closed network, in an enterprise network, I would dearly love to get my hands on some of these traffic and implement the algorithm on it. So one of the things we are doing is this scheme is going to be implemented on top of a real-life monitoring mechanism that is running on. We have a partnership with the South Korean government, and they're actually running the KISA, which is Korean Information Security Agency, is running a intrusion detection monitoring network on their national internet infrastructure. So this is one of the schemes that they're going to take it and actually implement on their network and see what it looks like. So I'm excited about that. Yes?
A quick question. For those host-based implementations, is it very easy to bypass by installing malicious drivers?
Well, so what you would do is you can implement this for instance, in a network card, and it's not easy to bypass.
Anything can be bypassed if you.
Yeah, ultimately anything can be bypassed. Yeah, but you can. What?
Rate limiting schemes, a lot of them are in the middle of the network.
But so if the thing is, if you do these rate limiting at a place that is somewhat separate from the core operating system, for instance, that could be compromised. You could do it in a network card or do it in a, I don't know, a separate server or something that is not actively connected to the network. Well, take that back. It has to be actively connected to the network. But in a network card, for instance, then you're shielding yourself a little bit from some of the common attacks. Yeah. Yeah.
Will you be making the results from the Korean government study public?
I'm sorry?
Will the results from the Korean government?
That we don't know yet. We have to talk to them. So the initial agreement is they're going to let us see at least the result of the data, and whether we can actually publish in a way that academics are satisfied with the results, that I don't know yet. Yes?
How much traffic was going through that egress router when you collected this data? What was the average?
In the first day, I have a slide. In the first day I think is 430,000 flows that going through outbound flows on the first day if the worm hits.
What about previous day?
Previous day is about. So it's about 20 times as much in the I can't do the math on top of my head.